Hello, in this video we're going to learn a technique for finding the volume of a solid of revolution. Now we have seen in a previous video how to find the volume of a solid of revolution using the disk and washer method, and in this video we're going to learn a new technique. But before we jump into this new technique called the shell method, let's review how to use the washer method. In our first problem here we have a region R formed by the functions f, g, and the y-axis, and we're asked to find the volume of the solid formed if we rotate this region R across the x-axis. So let's go ahead and indicate on our picture that the x-axis is our axis of revolution. Now notice that we do have some empty space between our shaded region and the axis of revolution, and that's how we know that we're going to have to use the washer method here. And the washer method really is just doing two separate disk methods and subtracting the results. And the reason for that is we find the volume of the empty space using the disk method. So to set that one up, here's my function g, right, which represents the area below g, and above the x-axis is that empty space. And so if I use my disk method, I can find the volume of this empty space right here that will, after we rotate, would kind of look like that. And we're going to subtract that from the volume that we'd be finding if we filled in that empty space and just found the volume of this shape right here, right? So we've got our outer solid region, and then we've got this inner region which represents empty space that we want to subtract away. So that's the idea behind the washer method. And because our interval is the same for both of these volumes, we can do this using just one integral. We don't have to do this as two separate disk problems. You can certainly, and you'll get the same result, but we can also just combine this into a single integral. So if you remember your basic setup for washer method, to find your volume, you're going to multiply pi by the integral from a to b being the interval that you're working on, of your big radius or your outer radius squared minus your inner radius squared times dx. So the pi big R squared dx represents the volume of the larger disk, and then the pi little radius squared dx represents the volume of the smaller, I said disk a moment ago, but well, yeah, disk, the smaller disk. This is just the empty space disk, and this is the whole thing as if we had filled in the empty space. So we combine them into one single integral. So when we're setting up this problem, I like to go ahead and draw my reference rectangles. So for the washer method, we draw one that goes from the axis of rotation to the furthest away side of our shaded region. That represents our outer radius. And then we draw another rectangle to represent the inner radius. And I like to draw it off to the side so it doesn't get in the way when I'm labeling things. But technically, that inner radius, should be drawn right here. It lines up with the outer radius. But again, I like to draw it off to the side just so it helps me if I have to start labeling things. I'm not trying to write one thing on top of another thing. All right, so my setup then for my volume here, it's going to be pi, and I'm going to integrate from x equals 0 to this x value right here, which I haven't found yet. So we're going to need to find this point of intersection so we know the integral that we are working on. So let's go ahead and switch over to the calculator and find this point of intersection. Okay, so using my calculator, I'm going to enter my two functions. I'm going to put f of x in y1. So this is 1/2 or 0.5 e to the x plus 1. And then my next function, g of x, I'm going to put in y2. So it's 3/2, or 1.5, times x squared. And I usually start by just trying zoom 6 and seeing if that gives me a decent window. All I'm really looking for is that point of intersection, so I don't need to have the best window here. I can see the point that I'm looking for right about here. And so we're just going to go ahead and go into second calc. Number 5 is intersect. And then I'm going to move my cursor so I'm closer to this point of intersection than the other one, and I'm going to hit enter 3 times. Enter, enter, enter. And so I have the point of intersection 1.200 and 2.160. So let's go back and label that on our graph. And so we know that this x value is the 1.200, which I'm just going to write 1.2 there. So our interval, this is a dx problem, and I know that because the width of my rectangles is the change in x. So these are x values. We're going from x equals 0 to x equals 1.2. And you should round to 3 decimal places, but since I have zeros in the second and third decimal place, I'll just write 1.2. Now we want the outer radius, which is this vertical distance right here. So I do the top y, which is f of x, y equals f of x, minus the bottom y, y equals 0. So f of x minus 0, that vertical distance is just f of x. So it's f of x, and then I square my radius. Minus, now we go to the inner radius, and again we want this vertical distance. So the top, it's the top y minus the bottom y. The top y is touching y equals g of x, and the bottom is y equals 0 again. So this is just g of x, and we square that inner radius. And then we multiply that difference by dx, and there is our integral. So we have our problem all set up, and now to actually do the integration, we're going to go back to the calculator. So I'm going to quit to go back to my home screen, and then we'll go ahead and compute our integral. So the first thing we want is the pi, and then for the integral, we're going to hit math 9. And then we're going to enter our bounds. So it's from 0 to 1.2. And then you can type out the equation here if you like, but since I already have it stored in y1, it's easier just to call up y1. So I'll do alpha f4 y1 squared minus, and now I want to call up y2, so alpha f4 number 2 for y2, and square that times dx. And our final result, 5.005. And so we have that is approximately 5.005. Now let's consider this next problem. Consider the region bounded by the function y equals sine of x and y equals 0 between x equals 0 and x equals pi. So we're talking about this region right in here. Is it possible to use the washer method to find the volume of the solid formed by rotating this region about the y-axis? So if we want to rotate around the y-axis using the washer method, we know that we have to draw the reference rectangle perpendicular to the axis of rotation. So the outer radius would look something like this for our rectangle there, and then the inner radius something like this here. Now this is problematic for us because notice that whether I'm thinking about the outer radius or the inner radius, the right side of the rectangle is still just touching that same equation, right? So if I tried to just do this function right here, if I might call it f of x, right? So if I do f of x, well, no, it's got to be f of y, right? Because now it's a horizontal rectangle. So f of y minus, and then right here we've got x equals 0. X equals 0. So we have x equals f of y, and we have x equals 0. But over here, we also have, right here, x equals f of y. It's the same function. And then here we have the x equals 0. So we certainly don't want to set it up by saying it's f of y minus 0 squared minus f of y minus 0 squared, because that's just going to give us 0. So we have to think really carefully about what's happening here. And the problem is that x is not a function of y. When we look at this graph, we have y is a function of x, and we can see that on the graph because we know that this graph passes a vertical line test. No matter where we draw a vertical line, we're only going to be intersecting the graph in one spot. So we can clearly state that y is a function of x. However, if we invert this or think about it going this way, then x is not a function of y because we fail the horizontal line test. X is not a function of y. And that means that when I write x equals f of y, I'm not guaranteed that when I substitute in one y value, I'm only going to get out one particular x value. So I shouldn't even use this notation because x is not a function of y. So I shouldn't be using function notation there, unless I have a way to define this as a piecewise function, which is ultimately what we would need to do if we're going to try and do Washer method. And what I mean by that is you have to break this equation up into two parts. You'll have this left-hand part of the equation, and then you'll have this right-hand part of the equation. And so when you write your equation, you're actually going to have two different equations, one for the right side of the graph and a different one for the left side of the graph, which is pretty complicated. And our function y equals sine of x, in order to solve that for x, we're going to have to use arc sine or inverse sine. So that also is making this really complicated. So somehow we would have to do an inverse function, and then we would have to write this as a piecewise defined function. It's just going to be really difficult to try and do this using Washer method. So thankfully we have a different method we can use instead. And let's just reiterate one more time how we know Washer method is not a good choice here. And there's two indicators that really stand out to me. The first one is I can see that if I try to draw a horizontal rectangle, that the right and left side of these rectangles are touching the same function. That's not what we want. If we go back to this previous problem, notice when I drew my two rectangles, the top of the rectangle for the outer radius was touching f of x, and for the inner radius it was touching g of x, two different functions. So here we don't have that situation, and I can see we don't have that situation because I'm failing this horizontal line test here. The other thing that's problematic is when I look at the equation y equals sine of x, it's difficult to solve that equation for x. So that would be another reason why you might want to avoid using Washer method. When you use Washer method and you have a horizontal slice, you're going to have to solve your equations for x, and sometimes that's difficult to do. And let's say we were rotating around the x-axis instead. Sometimes it's difficult to solve an equation for y. The equation might be presented to you in the form of x equals, and it might be difficult to solve for y. So those are two different things you can use to determine whether you should be using Washer method or maybe trying some other method instead. So let's look at a quick demo just to see what would happen if we rotate a vertical slice or vertical cross-section around the y-axis. Like, what shape is that going to produce? What is that figure going to look like? Versus if we do a horizontal slice instead. If we do like tried to do a Washer method here, what is that going to look like if we rotate that shape around the y-axis instead? So we're going to start with horizontal slices, and we're going to rotate around the y-axis. So this will be Washer method because we are going perpendicular to the axis of rotation. So we have our rectangle, it's being rotated around the y-axis, and we are getting a circular washer. It's called a washer because it does have the hole missing in the middle, and that's that empty space between the region and the y-axis. Okay, so that's the shape that we get when we use the Washer method with a horizontal slice rotating around the y-axis. And think about how you would find the volume of that shape, of that disc. Now, let's consider this same region if we were to use a vertical slice instead, still rotating around the y-axis, but now our slices are parallel to the y-axis. So we're going to rotate that around the y-axis, and look how the shape has changed. It's no longer that same type of circular disc. Now it looks more like a cylinder, but a cylinder doesn't have thickness to it. So because it has some thickness, we're calling it a cylindrical shell. A cylindrical shell. But to find the volume of this shape, we're going to take the lateral surface area of our cylinder and multiply it by thickness. So no matter which one of these methods we use, we're still going to get the volume of our solid. And I'll let this one finish playing out so you can see what the volume of the solid looks like. So we could do this using washer method, although we've talked about why it would be very difficult to do. And we're going to now develop this new technique, shell method, so that our calculation is much easier. Okay, so here we go. We've got this f of x, y equals 0, x equals a, and x equals b forming our region. And I'm just going to shade it here for a moment so we're clear about what region we're dealing with. This is our shaded region that we are going to rotate around the y-axis and try and get the volume of this solid. So we're going to set this one up so that our reference rectangle is parallel to our axis of rotation. So the y-axis is our axis of rotation. We draw our rectangle parallel now, not perpendicular, parallel. And the thickness of my rectangle is dx, so this is going to be a dx integral. And then the height of my rectangle is just the top y, right? That's y equals f of x, minus the bottom y equals 0. So this distance here is just f of x, the height of that rectangle, f of x. Write an expression for the volume of one shell. So let me just kind of trace out what one of these shells is going to look like. We saw this in the animation, but this rectangle gets rotated. So if you're trying to draw it, you want to just kind of reflect your rectangle across your axis of rotation, and then just kind of try and draw it so that it's circling around like so, right? It's got some thickness to it. And then we'll just bend that to give it a little bit of perspective. So we've got this cylindrical shell. And we want the lateral surface area, this lateral surface area here of our shell. And the lateral surface area of a cylinder is 2 pi radius height. 2 times pi times radius times height. So we have 2 times pi times the radius, and now the radius of this cylinder would be this horizontal distance right here. So the radius, that horizontal distance. What is that horizontal distance? Well, we know for horizontal distance, we take the right x value minus the left x value. So the right x value, right here, this is the point x comma y. It's just x. We in general, we can just call it x. This x value, though, we specifically know that it's x equals 0. So this distance right here is just x, which hopefully makes sense to you, because if I said I want you to plot the point x comma y, what would you do? Well, from the origin, you would go over x and up y. Over x and up y. So the horizontal distance is just x. The vertical distance is just y. Okay, so the radius of our cylinder is just x, and then the height of the cylinder is this distance right here, which we said was f of x, 2 pi x f of x. So that's not volume, right? That's still just surface area. That's a two-dimensional calculation. So to get the volume of this shell, we need to multiply that lateral surface area by the thickness, and the thickness was just whatever width this was right here, the dx. So we multiply that by dx, and now we have volume. That is the volume of one shell. So let's go ahead and write that over here. It's the volume of a single shell, 2 times pi times x times y. But I'm going to write the y as f of x so that we're just using a single variable here, times dx. But it's basically just 2 times pi times x times y times dx. And then if we want the volume of the solid, we have to add up all of these shells. And we do that using an integral. So we are going from x equals 0 to x equals b in this case, 2 pi, and the 2 pi is a constant multiple, so we can bring that out. I didn't leave a lot of room, but we can bring that to the outside, or not. You can leave it in if you prefer. X, f of x, dx. And that is our formula for shell method here. Notice that in this method, we're not squaring anything like we did when we used a disk method or a washer method, because there our basic setup was area of a circle, pi radius squared, that's where the square came in, times the thickness. But here it's different. We're not doing area of a circle, we're doing the area of the side of a cylinder, and that doesn't involve squaring anything. So 2 times pi times radius times height, which translates into 2 times pi times x times y. And now we can go ahead and solve this problem. So we know that the equation is y equals sine x. Our interval is going from 0 to pi, and we're rotating around the y-axis. So my volume, and I do always like to draw my reference rectangle. So if I'm doing shell method, I'm always going to draw parallel to my axis of rotation. And I'm just, sort of randomly choosing where I'm drawing my rectangle. I don't want to draw it like all the way over here at the end. It's going to be super tiny. And I usually just draw it somewhere in the middle. I didn't go exactly in the middle this time, but a lot of times I do just put it in the middle. It's wherever you want to draw it. It's just there as a reference. We know that there are actually infinitely many rectangles in here when we do this for real. We're just drawing one of these rectangles to help us with the setup. So rotating around the y-axis, we have our reference rectangle, and our volume is going to equal 2 times pi times the integral from x equals 0 to x equals pi. That's the interval I'm working on. It starts right here and it ends right here. And then I also, when I'm doing shell method particularly, I like to draw the cylinder. It helps me figure out what to use for my radius and my height. So I reflect my rectangle over the axis, just get an idea, of how far over to draw that. And then I just kind of roughly come in here and draw a cylinder like so. It doesn't have to be perfect. Again, it's just there for reference to help me set this up. So I know I'm going to do 2 times pi times radius times height. And the radius of my cylinder is this distance right here, which is x. It's taking me to this point, x comma y right here. And the height of the cylinder is y. But when I write my equation, I'm not going to write x times y and then times the thickness dx, because in a dx problem, you don't want to have y in there. If you have x times y dx, then you need to use multivariable calculus to solve this, and we're not ready for that. So we need to rewrite y in a different way. Well, what does y equal? We know what y equals. Y equals the sine of x. So instead of writing a y, we're going to write the sine of x. So volume equals 2 times pi times integral from 0 to pi x sine x dx. And that is my setup. If I calculate this integral now, I will have my answer. So I'm going to go back to the calculator in order to find the value of this integral. So from my home screen, we have 2 pi, and then for the integral, I'm going to use Math 9. We're going from 0 to pi, and we are integrating x sine x. And remember, whenever you use the sine, cosine, or tangent button on your calculator, You need to make sure you are in radian mode. I can see right from the top of my screen here that I am indeed in radian mode. And then times dx, enter, and there we have it, 19.739. So this equals 19.739, approximately. So here we have sort of a general formula for setting up shell method. Q is our region. It's bounded by the functions f of x and g of x. And we are going to revolve this region Q around the y-axis. So the setup here would be that volume equals 2 times pi times the integral from x equals a to x equals b, r of x times h of x. So the r of x is the radius of the cylinder. Right here, this is the radius. And then the h of x represents the height of the cylinder. Okay, so r of x, that radius, it's going to be a horizontal distance between the function itself and the y-axis. And then h of x is that vertical distance between your functions f of x and g of x. Rather than trying to memorize this formula, though, it's better to be able to look at the graph and get the setup from the graph, because every equation is a little bit different, and the setup, is going to have to be adjusted accordingly. Let's look at this next example. Find the volume of the solid formed by revolving the region bounded by the function y equals 2x squared minus x cubed and y equals 0 about the y-axis. So notice that it doesn't say to use the shell method or the washer method or the disk method. It's up to you to determine which method you want to use. And sometimes it doesn't matter. Like, it's equally the same amount of work either way. So when you look at this, if you want to try using the washer method, you can. However, this is another type of problem where it's going to be really, really difficult to do washer method. And I know that because if I try to do washer method, my outer radius is touching this function and my inner radius is touching the same exact function. So this is a problem where it's going to be difficult to separate the right part of the graph from the left part of the graph. Like, you're going to have to come up with two different equations. And just looking at the fact that y equals 2x squared minus x cubed, I definitely get a sense that it's going to be really difficult to try and solve that equation for x. In order to do the washer method here, you're going to have to solve that equation for x. And it's going to end up having a plus or minus in it, which is going to allow us to look at the right side of the graph separately from the left side of the graph. So very, very difficult to try and do this using washer method. I would strongly advise you just go with shell method right from the start. If we're going to do shell method, we're rotating around the y-axis, then we draw our rectangle parallel to the axis of rotation. So when I have a vertical rectangle, I know that this is going to be a dx problem. So in my setup right away, I can say it's 2 pi times the integral from x equals some value to x equals some value. And then at the end, I know I'm going to have a dx. And what do I have in here? My radius times my height. So that's my basic setup. And sometimes I like to go ahead and just write out this as a sort of template for myself and then go back and fill in what I need. So let's do the lower limit of integration and the upper limit of integration. This interval, because it's a dx problem, we're using x values to define our interval. We're going from x equals 0 to x equals 2. And then I'm going to go ahead and draw my cylinder. So I'm going to reflect that rectangle over here and just draw a cylinder. There we go. Here's my cylinder. So that's going to help me figure out what's my radius, what's my height. So my radius, again, just like we saw in the last problem, is x. It's just the horizontal distance from the origin over to a point on the curve. And this point on the curve, we can always label in general as x comma y. So the radius is x and the height is y. So this is x and this is y. But in a dx problem, we're not going to write y. We have to define y in terms of x. So the radius is just x, but the y is whatever this y is equal to. And we know what y is equal to from right over here. Y is equal to 2x squared minus x cubed. Now from here, I'm going to go to my graphing calculator to compute the answer. So I've already shown you how to do this on the calculator. I'm just going to go ahead and do this off screen and come back with the results. And I got 10.053. For this next problem, we're asked to find the volume of the solid obtained by rotating the region bounded by y equals square root of x, the x-axis, and x equals 9 about the line x equals -1. So let's call this the x equals 9. And this is our x equals -1 here. So our shaded region is this region right in here. And that is going to be rotated around x equals -1. Not the y-axis, but x equals -1. So this is a problem where we could use the washer method. It wouldn't be too difficult to use the washer method. If we're going to use the washer method here, we would be drawing our rectangles perpendicular to the axis of rotation, and so we have to solve our equation for x because we need to get a horizontal distance here for this problem. But you can solve this for x, it's not too difficult, and go ahead doing washer method. But we're here to practice the shell method, so let's use that one instead. If I'm doing shell method, I'm going to draw my rectangle parallel to my axis of rotation, and my axis of rotation is a vertical line, so I'm drawing a vertical rectangle, which is going to make this a dx problem. So my setup volume equals 2 times pi integral from x equals something to x equals something, and then we have radius times height times dx. So let's determine our interval because it's a dx problem. Where does your shaded region start? Well, it starts here, not at -1, but it starts here at x equals 0, and it ends here at x equals 9. So we're going from x equals 0 to x equals 9. And then I'm going to draw my cylinder. So I'm going to reflect my rectangle, or try and visualize reflecting this rectangle across, not just the y-axis, but across the axis of rotation. So I'm trying to get that distance the same here on both sides. So it's about like right there. So it's about right there. That's it reflected across, and then draw my cylinder. Okay, so now the radius, be careful here, because now the radius is not the distance from the y-axis to the rectangle. Remember, it's the distance from here to the rectangle. So it's this distance right here, and that's not x anymore. In the last two problems we looked at, that distance was just x. The x is the distance from the y-axis to the rectangle. That's not what I need. My distance is bigger than that. I have to go starting at -1 and go all the way to the rectangle. Right here is x equals -1. We want horizontal distance. And so, like I've said in my previous videos when we were talking about washer method, if you want a horizontal distance, you're going to take the right x value minus the left x value. So this point that the rectangle is touching on the curve, we can think of that in general as the point x minus y. So that right x value is just x, and the left x value is always -1. That's fixed. That's not changing. So it's going to be x minus -1. That's the radius of my function now, x minus -1. And x minus -1 can also be written as x plus 1, that double negative there. And hopefully that makes sense, because going back to our picture, if the distance from the y-axis to the rectangle is x, then the distance from -1 to the y-axis is 1, then that total distance is x plus 1. So that is our radius. Now the height is a little bit easier. Generally, it's the radius that confuses people. The height of the cylinder is just this distance here. So top y minus bottom y. The top y is y, the bottom y is 0, y minus 0 is y. So this distance here is just y. And we want to rewrite that though, y equals the square root of x. So instead of writing a y here, I'm going to write the square root of x. Okay, so it's x plus 1 times the square root of x. And let me just rewrite this. So our volume is 2 pi integral from 0 to 9 x plus 1 times the square root of x times dx. That's our setup for calculating the volume. Now I'm going to go to my calculator off screen and compute the answer. And this is an integral that we could do by hand, but in this lesson I'm really focusing on setting up the method properly. So we're just going to do the integration on the calculator. And our volume is 723.823. Next, find the volume of the solid formed by revolving the region formed by y equals x minus x squared and y equals 0 about the line x equals 2. So to be clear, let's shade our region. It's the region under the curve and above the x-axis here. We want to rotate that now around x equals 2. So here's our axis of rotation. This is one that's going to be very difficult to do using the washer method for the reasons we've talked about before. It's difficult to solve that equation for x. It's not impossible. You could try completing the square on the right-hand side to solve for x. So it's not impossible, but it would involve a piecewise equation in the end, and that's going to make it much more difficult. So let's go with shell method here. We're going to draw our reference rectangle parallel to the axis of rotation. And we want to get our basics set up, which is volume equals 2 pi integral. And then what is our interval? So the interval is just establishing the shaded region. You don't go all the way over to your axis of rotation. It's just where do you start drawing your rectangles? Where do you stop drawing your rectangles if we were to draw them all? So in other words, where does the shaded area start? Where does the shaded area stop? So the shaded area starts here at x equals 0. This is a dx problem because it's a vertical rectangle. So x equals 0, and we stop when we get to this x-intercept right here. So we have to figure out what that is. What is that x-intercept? Let's look at this equation, y equals x minus x squared, and find the x-intercepts. So we can do that by factoring this as x times 1 minus x, like so. And then if we want to let y equal 0, that's how you find an x-intercept. We have x equals 0 and x equals 1. So we already knew the x-intercept at x equals 0, and the other one occurs at x equals 1. Okay, and let me erase this because it's going to be in our way. And so we need radius times height times dx for our setup. So I'm going to draw my cylinder. I'm going to reflect it across the x-axis. So I'm looking at that, and not the x-axis, the axis of rotation. So I'm looking at that distance right there, and I'm trying to mirror that on the other side. So that's about right there. This is going to be a nice wide cylinder coming around like that, like so. Okay, so the radius of my cylinder, the radius of the cylinder, is the distance from the rectangle to the axis of rotation. That's the radius of this cylinder. So this is a little bit more complicated than the radius we had defined before. But think of it still as horizontal distance. When you're calculating horizontal distance, you take the right x value minus the left x value. So what is this x value right here? Well, this is x equals 2. We know that's our axis of rotation, and it's at x equals 2. So the right x value is 2. The left x value, what is this left x value? Well, if this is the point on the curve x comma y, that x value is just in general x. Okay, so a little bit tricky, but if you just think of it as right minus left, it's pretty easy to get it right on your first try. So right minus left is going to be 2 minus x. 2 minus x. Now let me try and explain that a slightly different way. because that does tend to confuse people a little bit. So I'm going to erase this mark right here. If I just said 2, the radius was 2. 2 is this distance right here from the origin over to here. That is a distance of 2. So I know that my actual radius is less than 2. And this distance right here, distance from the origin to the point x comma y, the point on my curve, that distance is just x. Now what we're actually interested in, the radius of our cylinder, is this distance right here. So it's 2 minus the x. 2 minus x is this distance right here, and that is our radius, 2 minus x. All right, now the height of our cylinder is just this distance right here, or on the other side, it's right there. So top y minus bottom y is y minus 0, or just y. It's just the y, but in a dx problem, we don't write y. We have to write what y is equal to in terms of x, and we know that from this equation right here. Y is equal to x minus x squared. So there is our setup for our integral. If we were going to integrate this by hand, we would FOIL those terms out and use our reverse power rule to integrate. I am going to go to my calculator off screen and compute this value. And we get 1.571 for our volume. So you can see that the answers vary pretty drastically. Like our answer for volume here was only 1.6-ish, and in the previous problem we looked at, it was over 700. So it just depends on the functions that you're working with. So it's really hard to just kind of look at the answer and get a sense of if your answer is correct or not. But drawing a well-labeled picture is really going to help you get it right on your first try. Now, just to recap, always draw a picture and label that reference rectangle. Label the rectangle, and I also recommend drawing the cylinder if you're doing shell method. It gets difficult to draw the discs when you're using disc and washer method, so I usually don't draw those, but with shell method, I almost always draw my cylinder. And then the key thing to remember is to always draw your reference rectangle parallel to your axis of rotation when you're doing shell method. For our last examples, we are going to try doing these problems 2 different ways, because sometimes, one method isn't necessarily easier than another. So here we're going to find the volume of the solid formed by revolving the region between y equals x and y equals x squared about the y-axis. Y-axis, so there's our axis of rotation, and we want to keep in mind that the top function here is the y equals x, and our bottom function here is the y equals x squared. So that's true in both cases. We want to keep that in mind when we're doing our setup. So first, let's try this using shell method, and then we'll try it again using washer method and make sure we get the same answer both times. So we are rotating around the y-axis, and I like to start by drawing my rectangle. So if I'm doing shell method, I want to be parallel to the y-axis, so my rectangle is going to be vertical. And that means this is a dx problem. I'm going from x equals 0 to x equals 1. So my setup, volume equals 2 times pi integral from 0 to 1. Now I'm going to draw my cylinder. I'm going to rotate it across, or reflect it across the axis of rotation, which is the y-axis, and then draw in my cylinder right here. So that helps me just make sure that I'm doing my radius correctly when I complete my setup. Okay, so now I need radius, and the radius is this distance here, which is x, and the height is this distance here, which now it's not just y this time. That vertical distance, you need to do the top y minus the bottom y. So the top y is y equals x, and the bottom y is y equals x squared. So our setup here, it's radius times height, x minus x squared. times dx. Okay, and that will give us our volume. Now, if we do this same problem using washer method, and I know it's going to be washer, not disk, because there is some empty space between my region and my axis of rotation. So I would need an outer radius, like so, and an inner radius. Okay, so my basic setup here is not 2 pi, but pi, and then radius squared, big radius squared minus little radius squared. So big radius squared, it's the right x minus the left x. Now this is a dy problem because it's a horizontal rectangle. So I need to go from y equals to y equals. Be careful there. And then it's a dy at the end. So I'm going from y equals 0 up to this point right here, y equals 1. So even like coincidentally, if you had accidentally used x values here, it would also be 0 to 1, but be careful about that. So y goes from 0 to 1, and then we need the big radius, which is this horizontal distance, so right x minus left x, and then on the right, x equals what? And on the left, x equals 0. On the right, x equals, well, this came from the equation y equals x squared, so you need to solve that for x. If y equals x squared, x equals plus or minus the square root of y. But because we're on the right half of the parabola, it would be the positive square root of y. So it would be square root of y minus 0 squared. That's big radius squared. Now, for little radius, we again have a horizontal distance, so we need to do the right x minus the left x. The right x here, well, that's coming from the equation y equals x. You solve that for x, you get x equals y. So it's y, the right is y, and the left x is 0. It's just y minus 0. So we do big radius squared minus little radius squared times dy. Now, if we did each of these properly, we should get the same answer both times. And when we work this out, we do, in fact, get the same answer both times. It's pi over 6 if you work it out by hand, or it's fine if you just checked it on your calculator. Okay, here we have y equals square root of x. That's the graph that we're shown. And we want to take the region formed by that function and the x-axis from 0 to 1. So that would be this shaded region right here from 0 to 1. And we are going to rotate around the x-axis, Try solving the problem 2 different ways, shell method and washer method. So let's go ahead and use the shell method first, like we did last time. Now, this is the first shell method we've done where we're rotating around a horizontal axis. So remember, when you draw your rectangle, you must draw it horizontally, parallel to the axis of rotation. So here's our boundary right here at 1. I'm going to draw my rectangle parallel to the x-axis, and that makes this a dy problem. So my setup, volume equals 2 pi. It's dy problem, so I'm going from y equals something to y equals something. And we can see in the picture here, we're going from this point is y equals 0 up to this point right here where y equals 1. So we'll go from 0 to 1. And then I need to sketch my cylinder. So I'm going to rotate my rectangle across the axis of rotation and draw the cylinder. So this time it is oriented this way. And now I need the radius of my cylinder. The radius is going to be this distance right here. So I usually go actually to the point where it's touching the curve, so the other side, but the radius, is still that same distance. So this is the point x comma y. Let's keep that in mind. The radius is now a vertical distance, and for vertical distance you do top y minus bottom y. So the top y is just y equals y, and the bottom y is at y equals 0. So the radius is just y in this case, is just y. Now the height of the cylinder is this horizontal distance. And for horizontal distance, we do the right x minus the left x. The right x is x equals 1. I kind of covered that up with my drawing, but that is at x equals 1. And the left x is just x. So 1 minus x. Now that's a problem because this is a dy integral. So I can't have 1 minus x. I have to rewrite this x in terms of y. So we know that this came from the equation y equals square root of x. That's what this function is. So we have to solve this for x. And we get x equals y squared. So I need to write 2 pi from 0 to 1 y times 1 minus y squared dy. We want to convert everything in terms of y. And if you go ahead and solve that, you're going to get pi over 2. So let's show the setup if we had done this using the other method. So I'll erase how I've labeled my picture. We're going to have to rework that. And now I'm going to use, so let's think about this. We are rotating around the x-axis, and there is no empty space between my shaded region and the x-axis. If I go back and shade that in again, there's no empty space, which means we don't have to use washer method. We can just use the disk method. And the disk method is the easiest probably of all the methods. Well, in most cases. We've talked about why it might not be a good idea to use disk method in certain cases. Okay, so if I'm doing disk method, I draw my rectangle perpendicular to my axis of rotation, making this a dx problem. And often dx problems are simpler to do than dy problems. Not always, but usually. Okay, so we have pi, and then we just need radius squared. The radius being this distance right here. So it's top y, here, y equals square root of x. Top y minus bottom y. The bottom y is y equals 0. So it's just square root of x squared times dx. That's it. And that one, let's go ahead and work that one out by hand. Oh, and my bounds would go from x equals 0 to x equals 1. So pi times the integral from 0 to 1. The square root of x squared is x. So you just have to integrate x. You get x squared over 2 from 0 to 1 times pi. You sub in the 1, you get 1/2. You sub in the 0, you get 0. So this is pi over 2. So this problem was a lot easier to do using the disk method, in my opinion, than the shell method. But you can see that both methods do work, and they give you the same result in the end. And our final example, here we have the equations x equals y cubed and y equals x. So y equals x would be the linear one down here. There's y equals x, and there's x equals y cubed. And we have the region going from y equals 0 to y equals 1. Y equals 0 up to y equals 1. So there's our shaded region. And we want to rotate this region about the line y equals -1. So here's our axis of rotation at y equals -1. Try solving the problem 2 different ways. So here we can do shell method, and then we will do washer method. We won't be able to use disk method on this one. All right, so starting out, if we do use the shell method, I'm going to draw my rectangle parallel to my axis of rotation. And because it's a horizontal rectangle, I know I have a dy problem. So volume equals 2 pi integral from y equals 0 to y equals 1. Radius times height times dy. I'm going to draw my cylinder to help me figure out my radius. So my cylinder comes down like so. And the radius would be this distance here. It's a vertical distance, so I'm going to do top y minus bottom y. The top y right here is just y. If that's the point x comma y, I'm just going to call that y. The bottom y right here is -1. And so my radius is going to be y minus -1, which turns it into y plus 1. Then the height of my cylinder, now this cylinder is sideways, but the height of the cylinder would be that distance, and that's going to be the right x minus the left x. So we need that horizontal distance, and the right x is just the x value on this function, and the left x is just the x value on this function. So we're going to have to find expressions in terms of x. Well, we already know that right here, x equals y cubed. That equation was given to us. And then right here, sorry, this is getting a little bit messy, but that is touching the equation y equals x, and so we know x equals y. So we're going to do the right x minus the left x. We're defining our x values in terms of y because it's a dy problem. So the right x is y minus, and the left x is y cubed. Okay, so there's our setup using shell method. Now I'm going to erase my drawing and set this one up using washer. So for washer, we draw our rectangle perpendicular to that axis of rotation. Now I know this is a dx problem. So volume equals pi. And then I'm going from x equals 0 to x equals 1. And by the way, it is just a coincidence that these last few problems, the x bounds and y bounds have been the same. That is generally not the case. But here it is, happens to be true. So pi, and then I need outer radius squared minus inner radius squared. So the outer radius squared, here I'm going for the top y minus the bottom y. The top y is x equals y cubed, so we have to solve that for y. If x equals y cubed, then y equals the cube root of x. And the bottom y is y equals -1. So top y, cube root of x, minus the bottom y is -1 squared. With washer method, we square. We're doing radius squared. Big radius squared minus, now we need to do the same with little radius squared over here. So the top y is y equals x, and the bottom y is y equals -1. So that radius, x minus -1, we square that little radius. And then all of that gets multiplied by dx. So here's the two different setups. And when you work both of these out, you should get the same answer in the end, which is 23 pi over 30. Now you're not going to get that exact answer unless you work it out by hand. So if you checked it on your calculator, that's fine. You would just have a decimal value there instead. So critical thinking, something for you to think about after this lesson. When is it easier to use the shell method rather than the washer method to calculate the volume of a solid? There's a couple different reasons that we've talked about in this lesson. So think back on that when you're looking at a problem. How are you going to decide which method to use? Because oftentimes you will not be told, I think probably all the time, you will not be told specifically which method to use. It's up to you to decide which method is going to work out to be the best for you. So these methods do take a little bit of practice, but stick with it and you'll be fine. Thanks for tuning in, and I'll see you next time.